So it's a great pleasure to have Dick Gross from Harvard, of course, here today. And I've been told that I can just say that he's going to talk about parawhorics and supracuspidal representation.
Thank you. Thank you, Chris. So it's nice to see everybody. And I see you all have assigned seats, and you spend about 8 hours a day in this room on these lectures. So thank you for coming to mine. So I want to talk about some work I've been doing with Mark Reeder and Ju-Kang Yu to try to understand a little bit better some supracuspidal representations of groups over local fields. So I'll let K be a non-Archimedean local field. And the ring of integers I'll denote by A, and a uniformizing element by pi. And the residue field A mod pi should be finite of order Q. And just because I don't want to go into the whole business of parawhorics, I'm going to do the simplest case where G is a split and a simply connected algebraic group over K. So some examples would be SLN or the symplectic group, or if you like to do exceptional groups, G2 or E8. The idea is to try to provide something that works uniformly for all the simple groups. And well, then the group of points is a locally compact group. And if I take a split group, I can define it over the ring of integers A. And so the locally compact group contains the points over the ring A, which is a compact open subgroup. And this reduces mod P to the points over the finite field, like G of Q or something. And using the structure of reductive groups over finite fields, you can define subgroups of this. For example, this contains a Borel subgroup over the finite field, and that contains a normal subgroup, which is its unipotent radical. And if you take the pre-images of those inside of this compact open subgroup, you get a subgroup which is called an Iwahori subgroup of G. And then it has a normal subgroup, which I'll just denote by U, or U of I, which is the pro-unipotent radical of the Iwahori subgroup. So this quotient is a torus, a split torus over the finite field, and that's the same as the quotient here, a finite group of order prime to P, and U is the pro-P CELO subgroup of the Iwahori. So this is a finite P group, and this is a pro-P subgroup of the points. Now, if you have there's a method of constructing representations of these p-adic groups that's called compact induction. If you have a compact open subgroup of G of K, and you have a finite dimensional representation of K on a complex vector space, finite dimensional, and then you can construct an induced representation by taking the functions, space of functions, let's call this the induced representation from K of M, and the functions from G of K to M that transform when you left multiply by K, transformed by this representation. It's rho of K, f of G. And if you have such a function, then it's supported on various cosets of K. If it's non-zero on one element, it's non-zero on the other elements in the coset. And we want the compact induction is where this is supported on finitely many cosets. So this is a completely algebraic notion. The compactly induced representation is a direct sum over the cosets of K of copies of M, which are permuted around by the group. And so it doesn't have to be a complex representation. You could do this over the rational numbers if you wanted to. So that's the definition of the compactly induced representation. And the group G acts on such functions by right translation. That gives a representation of the group. And usually that's it's very rarely an irreducible representation of the group, and you're always delighted if you're able to construct one when it is irreducible. So to give you an example when it isn't, you might take the trivial representation of K. And for example, if K were this compact open subgroup GA, this hyperspecial compact open, that would be a representation which contained all the unramified representations, all the representations that had a GA fixed vector. And there are a lot of unramified representations, so that's very far from being irreducible. But an example which I like very much is if instead of taking the trivial representation of GA, you take a cuspidal representation of this quotient. So if you map K, which is GA, to G of Q, and then you take a representation of this into GLM, which is cuspidal and irreducible of the sort that were constructed by Deligne and Lustig. So for example, if you took the group SL2, these would, maybe you take a representation of dimension Q minus 1 of SL2, and then you take those induced representations. Those are typically irreducible representations. They certainly have finite length. So for a sufficiently complicated representation of this group, you do get very interesting representations of the p-adic group, and the irreducibles in this induced representation were analyzed by Reeder and de Backer. And more generally inducing from other maximal parahoric subgroups. And they showed that their Langlands parameters were the parameters that were tamely ramified parameters. Tamely ramified discrete parameters. Which is a nice collection of representations. But I was interested with Mark in exploring representations where the parameters were discrete parameters but were wildly ramified. These are what are called depth zero representations. What about wildly ramified? Well, the first nice examples which Mark constructed went the following way. He took these are the what he called simple supercuspidals. And they are, in some sense, simpler, even simpler than these representations, because these look pretty reasonable, but you have to first construct the cuspidal irreducible representations over finite fields, and that's quite a theory. So how about this? You take, instead of inducing a representation of this GA, we're going to induce a representation of the pro-unipotent radical of the Iwahori. So we're going to induce a representation from the pro-unipotent radical of Iwahori of a character. So this is a one-dimensional representation. So a one-dimensional representation of a pro-P group is going to be a homomorphism into some p-power roots of unity. And in fact, I want a homomorphism from U into mu p inside of the complex numbers. And if you have a homomorphism from a pro-P group into mu p, then it factors through what's called the Frattini quotient, which is the quotient of U by its closure of its commutator subgroup and the pth powers. So this is the maximal elementary abelian quotient of your pro-P group, and that's a vector space of finite dimension over the finite field, over the field of P elements, if and only if this is a finitely generated group. It's like a non-commutative form of Nakayama's lemma. And so if you wanted to describe characters of this group, you would want to know, what is this group? So I have to say that we don't know this in general for small primes P, but we do know a quotient of this. Namely, this always maps to, that U always has a quotient which is the direct sum of, over the field of, it's a vector space over the field of Q elements, a direct sum of copies of FQ, and which as a representation of this finite group which normalizes it is the direct sum of characters where alpha is a simple affine root for T with respect to some ordering. Namely, there's a quotient of this, which is an FQ vector space, and this has rank, this has dimension n plus 1 over FQ, where n is the rank of G. And you can decompose it into lines by the action of this torus, and the lines correspond to the simple affine root spaces for T of Q. Now, T of Q may be too small. I mean, if Q were the field of, if Q were 2, this is the trivial group, so it doesn't decompose at all. So if you really want to decompose it into lines, you have to make an unramified extension and then decompose there where you have enough characters of the torus, but I'm going to ignore that for the moment. And then, so you get a character by first mapping it down to this, which we believe is the Frattini quotient. In any case, I'm going to write this as U mod U plus because it is a quotient in what's called the Moy-Prasad filtration of this pro-unipotent radical. I mean, it's the first step in the filtration. And then you take a character that maps you into mu p like that. Now, the simple affine roots, what are they? Well, I'm not going to give a course on affine roots here, but if you were in the group SLN, for example, the simple roots, as you know, are the, for the standard choice of the Borel, are the character spaces just above the diagonal. And then the lowest root, which is the last simple affine root, would be that root. So you get those. So this space is a little larger than the torus. And we'll call a character that we're going to study an affine generic character if when you view it as a character of this vector space, it's non-trivial on each one of these lines. So you say psi is affine generic. I'll give an example in a minute. If non-trivial on each line FQ alpha. So that's a generalization of what we call a generic character of the unipotent radical of the Borel. People have studied characters of unipotent radical of the Borel where the abelianization is the direct sum of the simple roots, and you ask that the character be non-trivial on each simple root space. Well, here we demand that it be non-trivial on each simple affine root space. All right, and if you make that hypothesis, and then you find, then this representation has finite length, and it's a direct sum of Z of Q irreducible supercuspidal representations where Z is the center of G. And in fact, the way you get this many irreducible supercuspidals is that you discover that the stabilizer in T of Q of an affine generic character is precisely Z of Q, and then you extend your character in this many different ways to use semi-direct product Z of Q, and then you induce from this larger group, and that turns out to be an irreducible representation. So it decomposes in the simplest possible way. You get an actual semi-direct product because this group is of order prime to p. So you take this character, you extend it to the centralizer, and then you induce, and that's irreducible. And those are the simple supercuspidal representations. It works in general for any group. So I'll give you one example which I like very much, just to show you that it's surprising. So let's take the simplest group and the simplest local field. We'll take the group G to be SL2, and we'll take the local field to be the two adic numbers. Okay, so then the Iwahori is the subgroup of matrices A, B, 2, C, D, where A, B, and C, D are such that A, B, C, and D are in Z2, and the determinant is 1. Right? That's the subgroup of the... Okay, now we have to take the unipotent radical, by the way, is exactly the same thing. Because in this case, the torus is a split torus over the field of two elements. So this group is equal to this group, and the Iwahori is equal to a unipotent radical. So that was easy. We didn't have to worry about the torus action there. OK, but on the other hand, we happen to know what the simple affine root spaces there are above and below. So we need a character which is non-trivial on those spaces mod 2. And so the only possible character is that chi of AB 2CD is equal to minus 1 to the C plus D, because it has to be non-trivial on this mod 2, it has to be non-trivial on that mod 2. And there's exactly one affine generic character. In general, you have to count these things, and you know, even if you, and you only really care about them up to the orbit of the torus, but there are a finite number of them because the torus can't act transitively on this space. This space has dimension n plus 1, and the torus has dimension n, so you get about q minus 1 different characters. Well, q minus 1 is 1 here. So if you take this representation, this character, and you induce it to SL2 of q2, then since the center over q is trivial in this case, center of SL2 is a mu2, but over the field of 2 elements, there are no elements in mu2. So we get the induced representation from I to chi, which is pi, is irreducible. Okay, so there it is. What could be simpler than that? What could be simpler than that? Now, what's its Langlands parameter? For SL2, we happen to know the Langlands parameterization. I told you you'd get a wild parameter. Well, it's interesting. You get quite an interesting parameter for this representation, which shows that they're not that stupid. It's a supercuspidal, so the parameter has to be irreducible. And the parameter would be a homomorphism from the Galois group of Q2 bar over Q2 to the group PGL2C, which is the dual group of SL2. Well, it's going to factor through a finite quotient of the Galois group. And that finite quotient is going to be the Galois group of K over Q2. So it's going to surject down to there. And that's going to inject and be isomorphic to a subgroup of type S4 in PGL2. And there's a unique conjugacy class of S4 in PGL2. So we're going to have to construct, to make the parameter of this silly representation, an S4 extension of Q2. And the S4 extension turns out to be the splitting field of the polynomial x squared plus 2x plus 2, which is the S4 extension which is of minimal wild ramification. The discriminant of that is 2 to the 4th. And so if you take the splitting field of this, now that's wildly ramified. In fact, if you think of S4 and you take a filtration of S4, it has a normal subgroup, which is the Klein 4 group. Then it has another normal subgroup, which is the alternating group of order 4. And then it has a quotient of order 2. This is the wild inertia subgroup. This is the tame inertia subgroup. And that's the unramified quotient of the Galois group. So already in this very simple representation, we get an interesting Langlands parameter. And we could figure that out by matching the formal degree of this representation and some facts about the formal degrees of parameters for GL2. OK, so this was the first construction that gave us some hope. Now, this lecture is about the following problem. This is just the Iwahori and its pro-unipotent radicals, an example of what's called a parahoric subgroup. And we wanted to know if this kind of construction worked more generally for other parahoric subgroups. So that's what I'm going to do. Pierre? Well, it's Z of Q is just the points in T of Q that stabilize the character. So.
But can't you extend the character to the center anyway?
Yeah, but it's the center. You see, what happens is the points of the center which are not in Z of Q, namely which have p power order, are contained in U of Q. So it's already so that's an amusing thing. You see here, this character is already trivial on the center, right? Because that's contained. That confused me too. Okay. Good. Okay. So the other parahorics, and we're going to see. So it turns out that this works for some parahorics, but not for all of them. And figuring out which parahorics it works for was a fascinating problem, for us at least. So without giving a course on the building, which I'm not totally capable of doing in any case, I'll just say the following. We have the Iwahori subgroup of G of K, and we found one subgroup G of A that contains it, and this happens to be a maximal compact subgroup. Now, what Bruja and Titz discovered was that there were other maximal compact subgroups that contain the Iwahori, and in fact, they're exactly n plus 1 maximal compact subgroups containing I. And in the, so maybe I'll call them Ki or something, I don't know. And they're indexed by the vertices of the extended diagram. Pardon? N is the rank of the group. Sorry, I meant to say that. Rank of G. And so they're indexed by the vertices of the extended or the affine diagram. And the extended vertex corresponds to GA. Maybe call this one K0 or something. K0 to the extended vertex. And not only that, but these n+1 maximal compacts that contain the Ihori represent the conjugacy classes of G on the maximal compact subgroups. Beautiful theorem. In the real group case, there's only one conjugacy class of maximal compact subgroup, but in p-adic case, it's much more interesting because there are more conjugacy classes. And then you get a beautiful combinatorial structure by just taking the intersections of these. So you can define p sigma as the intersection of ki for I and sigma for any non-empty subset of vertices of the extended diagram. And these subgroups all contain I, obviously, which is the I turns out to be the intersection of all of them. And these subgroups that you obtain are called parahoric subgroups, and they represent the conjugacy class of parahorics, whatever those are. So if you know the structure of the building, I stabilizes an alcove in the building, and these maximal compacts stabilize the vertices of that alcove, and these parahorics stabilize the various faces of the alcove. I don't really need that. What I do need is the structure of a parahoric. So we get a lot of subgroups of G of k. In fact, we get 2 to the n+1 minus 1 subgroups of G of k this way, and they get different conjugacy classes and things like that. So you have a lot of subgroups which are open and compact to work with. So what I need is the structure of the parahoric subgroups. And that's another beautiful theorem in Bruhat and Titz, that they're not just compact open subgroups, but they give the group, just like this, a structure over the ring of integers. So each p sigma gives a structure of G over A. So a model which has the property that its A-valued points are p sigma, are the points of the parahoric, just like that happened. And moreover, if you take the special fiber of this group scheme, and that's not necessarily a reductive group anymore. In this case, it is a reductive group. The special fiber just mapped to G of q. But in this case, there's a unipotent radical of the special fiber, but it has a quotient which is a reductive quotient, which is a reductive quotient associated to the parahoric, and you can read this group, or at least its derived subgroup, off the subset of the Dynkin diagram. So this is the reductive quotient, which in the case of the two cases to bear in mind, in the maximal compact case, the reductive quotient is the points over the residue field, and in the case of the Ihori, the reductive quotient is this points in the torus, and the reductive quotient always has rank n, and it's a reductive group containing the torus, etc. And so what you get from this is you get a filtration of these points which map to the points of the reductive quotient surjectively, and the kernel is what's called the pro-unipotent radical of the parahoric. And we've seen that now in two cases. This was the case of the Ihori, which mapped to the torus, which kernel was its maximal pro-p normal subgroup. This is a pro-p group. And in the case of the maximal compact, which maps to the points of the group mod p, the kernel of the thing's congruent to 1. So in GLN, the matrix is congruent to 1 mod p. That forms a pro-p group. OK. So the way we wanted to try to generalize this was to say, OK, if we take U sigma and we mod out by what we think is its Frattini quotient, but the first step of its the first step of the Moy-Prasad filtration, we call that V of q. That turns out is an FQ vector space finite dimensional, and it's a representation, and it's an algebraic representation of the reductive quotient h of q, just like we had in the Iwahori case. If you do this, by the way, in the case of the maximal compact, this u0 mod u0 plus or something, that's the Lie algebra of G over the field of Q elements. It's the adjoint representation. You take the matrices congruent to 1 mod P, you mod out by the matrices congruent to 1 mod P squared, you get the adjoint representation. But in general, you get a representation of this reductive quotient. And we wanted to know if there were characters of U that factored through this FQ vector space, such that when we took the induced representation, then we got something of finite length or irreducible, like we did for the Iwahori. So you can formulate that this way. You have this map from U of sigma, and then you project it to this quotient, which is V of Q. And then you take a linear form to FQ on this vector space, and then you compose that with a non-trivial additive character of FQ, and you get a character of this group, which you could try to induce. And everything depends on the choice of this linear form, right? I mean, we have to choose that intelligently. And if you think about it, the linear form is not what the really critical piece of data is. It's the h of q orbit on that linear form, because we're going to take the induced representation from U, and U is normalized in the group by p sigma. So if we take another linear form in the same orbit under h of q, we're going to get the same induced representation. So the question is, what orbits of h of q on v of q dual give good characters? Well, if you ask it that way, you realize that you've fallen into the domain of geometric invariant theory, because that's what geometric invariant theory studies. It studies the orbits of reductive groups on their linear representations, and when are their open orbit, and when are there you call an unstable. Well, let's do a little GIT review. So we call an orbit unstable if the closure contains 0. This is David's notation. We call it semi-stable. We're not going to need any of this, but it's fun anyhow. If the closure doesn't contain 0, those are pretty good orbits from the sense of view of algebraic geometry. And then one way it couldn't contain 0 is if the orbit is closed. If it's closed, then it's not in the 0 orbit, it doesn't contain 0. And the best orbits are the orbits that are called stable orbits. And the stable orbits, which David came to a little bit later, were the orbits that were both closed and the stabilizer has dimension 0. The stabilizer is a subgroup scheme of H, and if it's a it's a finite group scheme, that's the best possible situation. So we realized after a while that what we were looking for were parahorics where there were stable orbits on this Frattini quotient where the reductive quotient had stable orbits on the Frattini quotient. And if you think about the case of the Iwahori, the characters which are affine generic, the linear forms which are non-zero on all of those lines, are precisely the stable orbits for the torus.
Is that because in these cases it's finite?
Yes, and
Not, but in the others it's not?
that's correct. We can show using some Mackey theory, Mackey's theories of induced representations and their decomposition, that we would get a representation of finite length precisely when we induced a character that came from a linear form in a stable orbit. So that was nice. But then the question was, what is the geometric invariant theory of this? So, for example, this is a little discouraging because, for example, for the group G of A, boy, you think G of A would be a good parahoric. What could be better than the hyperspecial parahoric? But for G of A, remember, the reductive quotient is G of Q. The Frattini quotient is the Lie algebra. The action is the adjoint representation. Now, there are closed orbits in the adjoint representation. Those are the orbits of semi-simple vectors in the Lie algebra. But there are no stable orbits, because the stabilizer of any orbit has dimension at least the rank of the group. Those are the regular orbits. So as nice as the adjoint representation is, absolutely no characters of this quotient in the hyperspecial case will give you these nice representations. So then the question is, when are there stable orbits? What is the geometric invariant theory of this representation on this? And more generally, as I said, there's a filtration of u of sigma, u of 1 over m, u of 2 over m. There's a certain integer associated to every paraHORIC. And we wanted to take any representation in this filtration, and that's a representation of this reductive quotient. And we wanted to ask, what are the orbits on V? Are there any stable orbits? What do the orbits look like? Are there any closed orbits? Anything. And when you think about it this way, it's a generalization of the theory of parabolic subgroups. If you have a parabolic subgroup in a group, and it's unipotent radical, and its unipotent radical has a filtration if you choose a co-character that gives you that paraHORIC. And you look at the action of the Levy factor in the paraHORIC on the various stages of that filtration, those are very special representations. They all have open orbits. That's a big theorem in Lie theory. So we thought, well, this is the paraHORIC. This is the affine case of that. Namely, we don't have a Levy factor. We have this finite reductive group. It's acting on quotients over finite fields. What is the geometric invariant theory there? And here's what we were surprised to find. Proposition. The representations V dual, which appear of HQ, of H, in the Moy-Prasad filtration, and in particular the first one, are all what is called co-free. Namely, if you take the symmetric algebra on V, the polynomials on V dual, and you take the H invariance, this is a polynomial algebra over FQ in a finite number of variables, P1 up to PR. It's a polynomial algebra. And another way of saying that is if you take the geometric quotient of V dual by H, that's affine space of dimension R. So it's the simplest conceivable geometric invariant theory. I mean, David developed this in cases where it was very difficult to decide whether you had closed orbits or not. So in particular, you have closed orbits. Closed orbits exist precisely when you have an invariant polynomial which isn't constant, when the rank is greater than 1. This R turns out to be some number between 0 and the rank of the group. In the case of the Iwahori, the rank is, so for this case, that's a famous theorem of Chevalley, that the adjoint quotient is a polynomial, is affine space, and there are n invariants, and they correspond to the invariant degrees of polynomials on G. And in the case of the Iwahori, the representation has dimension 1 larger than the torus that's acting, and it turns out there's R greater than or equal to 1. And it turns out there's a unique invariant polynomial, which is made out of products of the hyperplanes that vanish on those corresponding to those different lines. And so if you take the product of all those, it's non-zero precisely when you have a character that's non-zero on all those lines. So closed orbits exist precisely when this. Now then it becomes a question of figuring out for a given group and paraHORIC what the rank is. But at least it's a simple geometric invariant theory, and you know when you have a closed orbit or not. You don't know when you have a stable orbit, but you know when you have a closed orbit. So for example, we put this on the computer to give you an idea of what this is like. This is fairly rare. So for E8, there are 511 paraHORIC subgroups. Right? This is 2 to the 9th minus 1. And it turns out that 79 have for the first quotient here, for this V of Q, have a V of rank greater than or equal to 1, and almost all those, 59 of those, inside of the 79 have rank 1. And so you need a closed orbit to have a stable orbit, and it turns out that of these 79, exactly 12 have stable orbits. So I'll describe what I'm going to try to do is tell you where these 12 with the stable orbits come from. I have no idea how to distinguish these 79 from the other 511 until the computer does its printout. To give you an idea, if you like groups of rank 2, and I do, I guess I can erase this, huh? Here's the alcove for G2, which is a 30, 60, 90 right triangle. See if I can draw that. Well, that's close enough. This is the hyperspecial vertex, where the reduction is G2. I'll give you the reduction, the H. I'll give you H. Here the reduction is SL3. Here the reduction is SO4. On the edges, the reduction is GL2 for all the edges. And in the center, for the Iwahori, the reduction is a two-dimensional torus. So what are the representations? And when do they have closed orbits? And say, well, here the representation is G2, the Lie algebra. Here the representation V turns out to be the three-dimensional representation of SL3. So that's hopeless, right? I mean, zero's in the closure of every orbit in the three-dimensional representation, so forget about that. And here we saw what the representation was. And the parahorics that turn out to have stable orbits are this parahoric, that's the Iwahori, and this parahoric, which is non-maximal, and this maximal parahoric. And for this one, it's particularly beautiful, and Manjul explained the orbits to me. This representation, the V has dimension 5, and it's, well, if I write it as a representation I'll write it as a representation of GL2, Sim3, tensor, determinant, inverse, direct sum, the determinant. I believe that's the correct representation. It's not irreducible. So this is a four-dimensional representation, and this is a one-dimensional representation. And the invariant polynomial has degree 6. And what the invariant polynomial is it's the discriminant of this binary cubic, which has degree 4, and times the square of this vector, which is just a line, a coordinate on a line. So that's turns out that this representation has finite stabilizers for this group. And likewise, you'd have a representation there. So there it is, three of them for G2 work. OK, so which parahorics are good? All right, so let me introduce W, the Weyl group of G. So that's the normalizer of a maximal torus modulo the torus. It's a subquotient of the group. And I say an element in the Weyl group is elliptic if its fixed points on the character group of the torus is 0, no invariance. Or equivalently, if the character group of the torus modulo tau minus 1, which is the covariance for the subgroup generated by tau on the torus, is a finite group. So that's the definition of elliptic. And I say tau is regular. And this is a modification of a nice notion that was developed by Springer, which is a little simpler than his definition. If tau acts freely, or if the subgroup generated by tau acts freely on the set of roots phi inside of the character group of the torus. So inside of the character group of the torus, you have the roots, the characters that occur on the Lie algebra of G, and you have a finite set of them. And so any element in the Weyl group which acts on the character group permutes the roots around, and you want this to be a free action. Okay. Now, some examples of elements that are both regular or elliptic. Examples. You can take tau to be the Coxeter element. That's what's going to give us the Iwahori. So that's the product of the simple reflections in any order from 1 to n, and as a conjugacy class. This is really the characterization of conjugacy classes, because if tau is elliptic, then anything conjugate to tau, in particular any invertible power of tau, is elliptic, and same thing with regular. The Coxeter element. And another example, if you're lucky, if -1 is in the Weyl group, then it is regular and elliptic, because it's clearly elliptic in that it acts as -1 on the torus and on the character group, and it acts freely on the roots because it takes every root into its negative. Now, -1 isn't always an element in the Weyl group, and if you were at my lecture yesterday in Monjul's course, you'll know that we shouldn't be just doing this for the Weyl group, but we should be doing this for the automorphism group of the root lattice. And then, but if we did that, then I couldn't just work with split groups, but I'd have to work with quasi-split groups, which were ramified, and I didn't want to do that in this lecture. So I apologize for that. So you can always do something with -1, but I'll just do the case like E8, where -1 is in the Weyl group. And you can, by the works of Springer, you can make a list of all the conjugacy classes that are regular and elliptic. So for example, if you're in the group SLN, there are not many conjugacy classes that are regular and elliptic, because a conjugacy class is elliptic. The only conjugacy class is elliptic is the n cycle, because if it had 2 cycles in its decomposition, then on the permutation representation it would fix a 2-dimensional space, and this representation is the permutation representation minus the trivial representation, so it would fix nothing. It would fix a vector. So this is the only class, and that's the Coxeter class. So that always exists. -1 is only in the Weyl group here if n is 2, and that's when this is equal to the Coxeter class. But if you take a group like G2, then it turns out that the element of order 2, which is -1, and the element of order 3 and the element of order 6 are elliptic. And if you take E8, then there are 12 elliptic elements, and they have orders 2, 3, 4, 5, 6, 8, 10, 12, 15, 20, 24, and 30. And it turns out that a regular elliptic element, the conjugacy class, is determined by its order. Namely, there's at most 1 regular elliptic element of each order, and I'll tell you why in just a second. So that's a remarkable fact. So there are 12. And these 12 regular elliptic elements correspond to these 12 parahoric subgroups that have stable orbits, and these 3 regular elliptic elements here correspond to these 3 parahorics that have stable orbits. This corresponds to the element of order 6, this to the element of order 3, and this to the element of order 2. So the theorem is and I did this very briefly in Monjul's course yesterday, so for those of you who went to both lectures, I apologize, is that if you have a regular elliptic element in the normalizer of the torus, then, oh dear, now I realize I shouldn't have done simply connected groups. In the adjoint group, it lifts uniquely. So let me say it that way. So tau, regular, elliptic, in n of the Weyl group is the same for the adjoint group as for the If you have a regular elliptic element in the Weyl group for the adjoint group, then if you take any element in the coset of tau in the normalizer, all these elements are conjugate by the torus of the adjoint group, and they all have the same order, and the order is the same as the order of tau. All n in normalizer T add are conjugate by T add, all have order m, which is the order of tau. So if you restrict to this cyclic subgroup, you get a splitting of this sequence. And moreover, that you can say what this torsion, so you get a torsion class in the adjoint group. So we get theta, the conjugacy class of n in G add, and we think of G add as a normal subgroup of the automorphism group of our group. And this conjugacy class is now completely determined by tau, because if you conjugate tau and you lift, it's conjugate under the normalizer of tau, so it's conjugate under G. And we can identify this conjugacy class by using Katz's coordinates. And it's a remarkable conjugacy class. It's in the principal torus, is represented by the element rho check of e to the 2 pi I over m in G add, in T add, in G add. And where rho check is the co-character inside of the principal torus. And that's why there's at most one regular elliptic element for any given order, because there's only one subgroup of order m inside of the principal torus, and you show that those elements with the different generators are all conjugate in G. And it's Katz's coordinates. Katz gave a description of torsion elements in a group, and the Katz's coordinates of theta on the extended diagram are all 0 and 1. And in particular, the Katz's coordinates of the lift of this regular elliptic element in the Weil group determine a parahoric, determine a conjugacy class of parahoric subgroups, p tau or something. And our theorem is that these are exactly the parahoric subgroups which have stable orbits on any step of the filtration of the Moy-Prasad filtration. So that you get, and these have stable orbits, L in V dual for HQ, and so get induced representations of chi from U sigma or U tau or something of finite length. And these generalize the ones that we had constructed before, because every group has a Coxeter element which is regular elliptic. That's this element in the E8 case, and that's this element in the G2 case. And the parahoric subgroup, when you lift the Coxeter element and you find out what its Katz's coordinates are, they're all 1. And so that determines the Iwahori subgroup of your group. And so that's what Mark had constructed before. But now we have 11 more families for E8 and 2 more families for G2, etc. Now, moreover, I can tell you what's better than that. I said the stable orbits. What is the stabilizer? Remember, the stabilizer was supposed to be some finite subgroup scheme of G. And the stabilizer turns out to have Cartier dual. Stabilizer of a good vector has Cartier dual, the x dot of t mod 1 minus w. Remember I said that was a finite abelian group? So it's not just a finite stabilizer, and this is remarkable. It's a finite abelian stabilizer, which is in some sense even better, as Manjul and I have been thinking, than some of the stabilizers that come up in the prehomogeneous vector space case, which can be the symmetric group on 3 letters or 4 letters or 5 letters. These are all elementary. These are all very simple groups. So I said I would say a word about what the Langlands parameters are. I have a little time. Why not? one thing that's extremely amusing before I go to the Langlands parameters is that the families of affine generic characters that occur for the Iwahori are not so interesting. I mean, there's Q minus one of them, and you can parameterize them. But when you start getting down to the regular elliptic elements of small order, you get some really interesting geometric quotients that parameterize the characters. So, for example, for E8, if we take W equal to -1, then it turns out that the H turns out to be spin 16 mod mu2, and the V turns out to be a half spin representation. And when you take the geometric quotient of G mod H, it turns out to have dimension 8, and it's FQ, and the degrees are exactly the degrees for E8. There are 8 different degrees, and they're the same degree polynomials as the polynomials for E8. And you get these by restricting. By the way, I should say where this theorem comes from. I'm sorry, I should have said that. Namely, this identification of the geometric invariant theory of the Parahorix and the Moy-Prasad filtration with these polynomial rings or affine spaces comes from an essential bijection that we realized that the theory of Brouhat-Titz, which was developed in the context of p-adic groups or groups over local fields, is essentially equivalent in many aspects to the theory of Winberg, which was developed to study automorphisms of finite order of Lie algebras. And Winberg developed this theory in the 70s to generalize Chevalley's theorem about the adjoint representation, that the invariants were polynomial. And what Winberg showed was that if you had an automorphism like this theta of finite order of a Lie algebra, and that's why Katz started to classify the theta, etc. But if you had an automorphism of finite order of the Lie algebra, then you could or of the Lie group, then you could take the fixed points of theta in G, that would be a subgroup of G, and that acts on the Lie algebra, but it acts on the Lie algebra graded by the different eigenspaces for theta. And Winberg wrote this as GA, where A is taken mod M, but of course that requires the choice of an mth root of unity. I mean, this would be the eigenspace where theta acted by e to the 2 pi I A over M. It's better, instead of taking an automorphism of finite order, if you look at this, what you really have is a homomorphism theta from mu M into your group. And so we recast Winberg's theory that way. And if you have an automorphism of mu M into your group, then the Lie algebra really is graded by the Cartier dual of mu M. And this centralizer, whose Lie algebra is G0, acts on all of these submodules. And what Winberg proved was that every one of those representations was cofree. And what we were able to do was realize that this filtration of the pro-unipotent radical of a Parahoric was essentially given by an element of finite order where our H was the G theta, and the first step was G1, and the second step was G2, and the third step was G3. So from Winberg's theory on invariance and geometric invariant theory, we were able to deduce ours. Okay.
You know the length
Of?
these things that you get.
Oh yeah. Sorry, the length again. So let's call this stabilizer S of Q or something like that, because it was the center of Q before, and that's an abelian group, and the length of this is the order of that group, and it decomposes in a multiplicity-free way. And again, it's the same argument. You extend this character from the pro-unipotent radical to the unipotent radical semi-direct product of stabilizer, and then every induced representation is irreducible. Okay. So what could possibly be the Langlands parameters of this? And then I want to just say a thing that I find absolutely amazing, a recent result of Jiwei Yun, which globalizes all of this. So what did we do to produce these representations? Well, we took a a regular elliptic element in the Weyl group. And then, we chose characters, etc. But so we have a regular elliptic tau in the Weyl group. All right, so the parameter is supposed to be a homomorphism from the separable closure of K to the L group, which in this case is just the adjoint dual group, because our group was simply connected over C. So based on our formula for the formal degree and the fact that we can calculate the formal degrees of these representations, because we know the volume of this unipotent radical and we know the dimension of this representation, which is 1. So we could calculate the formal degrees, and we had a conjecture relating the adjoint L function in the formal degree, which was first put forward by Ichino and Ikeda and Harada, and we had a little refinement of it. We predicted 2 things about the parameter. First was that if you took the adjoint representation and you took the invariance of inertia, that had to be 0. So it was not just a discrete parameter. Discrete parameter means that the invariance of the entire Galois group on the adjoint representation are trivial. That means that the centralizer in this group is a finite group. But this is sort of inertially invariant. Inertially discrete, you might call it. That's the first condition. And when anything's inertially discrete, it has to be wildly ramified. Because if it were only tamely ramified, inertia acts through a finite cyclic group. And a finite cyclic group always stabilizes a vector in a semi-simple Lie algebra. For this to happen, there has to be wild ramification. And we predicted what the Swan conductor of the adjoint representation was. And the Swan conductor should be the number of roots divided by the order of tau, which I called m. And that has to be an integer because, remember, we insisted that this acted freely on the roots. Now, in the old case, this Swan, for Mark's representations, the order of the irregular elliptic class was the Coxeter number, and the number of roots divided by the Coxeter number was the rank. So that was our old case. But now the Swan conductor is larger because the order of this regular elliptic element is always less than the Coxeter number. All right, if you put these 2 things in and you insist that you have such a parameter, there's really only one thing that could possibly be. Namely, it has to, let's factor it through the Galois group of a finite extension. And let's take the ramification filtration of this. So you have the inertia subgroup, and then you have the wild inertia subgroup, and then you have the other quotients, right, of the, by lower ramification filtration. So the first thing is that that D2 has to be equal to 0, so that the thing stops, or D1, whatever, it's a group. And that D1 is therefore an elementary abelian P group, and it maps into the, oh, sorry, this is when P does not divide the order of W. I don't want to do it in the other case, that's too weird. So P does not divide the order of W. D1 maps into the P torsion in a unique maximal torus. So namely it maps into regular elements in the P torsion in the maximal torus. And 3, therefore the entire group has to normalize this torus. So the entire parameter goes into the normalizer of the torus. And if you map D1 mod D0, so D0 mod D1, let's try that better. That would be better. Into the normalizer of T hat mod T hat, well, that's the Weyl group of the dual group, right? But the Weyl group of the dual group, this is one of the wonderful things about Langland's duality. It's the same group as the Weyl group of the group. I mean, I think they're canonically anti-isomorphic if you want to be precise. And this is a cyclic group, right? This is the image of tame inertia. So that should map to the class of tau in W. And so previously, we had always had our parameters where tame inertia went to the Coxeter element in the Weyl group, and now it could go to any regular elliptic class. And these are the only possible parameters. This D2 is, I say, 1. But notice that they're wildly ramified. D1 is non-trivial. It has to be because it maps to regular elements, but it's not terribly wildly ramified. And when you work out the action on the Lie algebra, you'll find this Swan conductor, etc. Is that precise enough to go with? OK. I hope someone will write down all these parameters exactly. Now, I just want to end, as I say, I thought we were working on local fields. But there was a wonderful advance last year when three authors, Jiwei Yun and Baochun Guo and Joachim Heinloch, were able to show that if you took a simple supercuspidal representation in pure characteristic P, so now we take the case where K is of characteristic P, so FQ, and I'll write it like this, T inverse, characteristic P. And you take pi infinity to be a simple supercuspidal, and I'm going to insist that the center of K acts trivially. In fact, I'm going to write this as K infinity to indicate that it's the completion of something. Then Guo and Yun and Heinloth showed that there was a unique automorphic cuspidal representation pi of G over FQ of T, namely on P1. With this representation at infinity, with the Steinberg representation at 0, and with pi v unramified for all v not equal to 0 and infinity. So this is a bizarre, and very unexpected result, which was reminiscent of Katz's result where he makes a canonical extension of a representation of a local Galois group to a representation of the global Galois group. But this is really not the same because it's an amazing business. And not only that, they constructed this associated, then they constructed the associated L-adic represent. 0 means the point 0 on P1, T equals 0. This is P1. So you have the projective line. At infinity, you put the simple supercuspidal. At 0, you put the Steinberg representation. And then it turns out there's a unique way to fill it in with unramified representation, so it becomes automorphic cuspidal. And then they constructed the associated L-adic representation from pi 1 of GM over FQ, because it's unramified outside of 0 and infinity, into G hat. Well, it's a modified G hat, which Pierre knows how to do, of QL of mu p. Because this representation has to contain p roots of unity. That's what you need to define the pi infinity. And this is amazing because they show in most cases the image is, the Zariski closure of the image is in G hat, so they produce Galois representations with image F4 and with image E8, and this was all unknown to us. And I thought, well, that was just remarkable about this and Steinberg and supercuspidal, and I had predicted this using the trace formula. But then after I showed Jiwei these representations that were made from a regular elliptic class in the Weil group, he proved exactly the same theorem from regular elliptic tau in the Weil group. And again, you want this, maybe the stabilizer S of Q to act trivially, that there's a unique representation, and this is no longer Steinberg. This is a unipotent representation of the group. And not only that, he...
There's only one unipotent which will work.
Exactly, only one. And moreover, the nilpotent element in G hat, corresponding to this unipotent, is the nilpotent element in the dual group that Lustig associates to a regular elliptic conjugacy class in the Weil group. So Lustig has a bijection between regular elliptic conjugacy classes in the Weil group and unipotent elements in the dual. And the unipotent, and when you take the Coxeter element, of course, that goes to the regular unipotent element. But Yun had realized that. So this is the craziest realization of Lustig's correspondence possible, because it goes through automorphic forms. And then I think he also has the construction of the Galois representation. And this is beyond my expertise, and you should have him come down and speak on it. But it's a terrific piece of work. So thank you very much.